Alright, we're going to do another KP problem. We're missing our yield sign there. Equilibrium sign there. 1 mole of hydrogen and 1 mole of chlorine are allowed to reach equilibrium at different temperatures. H2 gas plus Cl2 gas yields hydrogen chloride gas. Under the first set of conditions, the equilibrium mixture contained 1.4 moles of hydrogen chloride and a total equilibrium pressure of 4.0 atmospheres. Calculate the Kp. So Kp, I see, I'm going to go write my expression. I have hydrogen chloride partial pressure squared over partial pressure of hydrogen times the partial pressure of chlorine. Under the first set of conditions, the equilibrium mixture contained 1.4 moles of hydrogen chloride. So I know that, and I know the total pressure. Looks like we're going to have to do some type of mole fraction. I can do some stoic, or I can do an ice table. I'm going to go ahead and do an ice table. At equilibrium, I know I got 1.4 moles of the HCl, which means my change was 1.4 moles, which would mean I start with 0 HCl, which makes sense. So I start with the 1.4. I know my change is 1.4 because I really had nothing to start with. They tell me at the beginning I have 1 mole of this and 1 mole of that. Using stoichiometry, for every 2 moles, I might have 1 mole of this, so I have 0.7. I'm using it, I got 0.7 of this that I also use. So that means at equilibrium I have 0.3 moles of each of those. I need to find the pressure, so I'm going to use a mole fraction. There's a total of 2 moles. So I might take 1.4 and the pressure of HCl over 2, which is going to give me, oopsie, I want the pressure, times the total pressure of 4. So 0.7 times 4 is going to be 2.8, I think. Atmospheres. Once again, the units in the Kp don't matter because as long as they're all the same, because Kp is unitless. I might do the same thing to find the mole fraction for. I might find my mole fraction for hydrogen, which is 0.3 divided by 2 times 4 atmospheres. Which is 0.6. Same for Cl, so I'm going to have 0.6. Times 0.6, that's a 6, maybe it's a 6. So 2.8 squared divided by 0.6 squared. Looks like I should probably have around 2 sig figs. I'm going to go ahead and do 2 sig figs. That's 22. So my Kp is 22. And that's how you do equilibrium expressions. Oh wait, there's a second part to this question. This is really B, not 1. Let's do the second part of this question. So we need to remember that we had 1 mole of H2 and 1 mole of Cl2 to begin with. At second temperature, the overall pressure at equilibrium is 7.2 atmospheres and Kp equals 2.11 times 10 to the 4th. What percent of hydrogen is converted to HCl? So that's a good question. So we know Kp. I need our equilibrium expression, which should be in P's, which was from the previous slide, HCl Gauss pressure squared over the pressure of H2 times the pressure of Cl2. Cl2. That's a Cl2. You just have to believe me. Cl2 Kp, they give us the value. Notice our Kp is really large, so we should get a high percentage. So let's see, let's go ahead and set up our ice table. We start with moles, so we'll go with moles. We don't know what our change is. It doesn't tell us. So we're going to say it's going to change by x. It's going to change by x. It's going to change by 2x. Those are both negatives for the changes in H2 and Cl2 because we're going to use them up and we're going to make 2x. So we get 1 minus x. 1 minus x equals, sorry, doesn't equal, gives us 2x. Let's see. This is going to give us our mole ratio. And since there's the same number of moles of gas on the left and on the right, we don't have to worry about anything. We can just plug it into our Kp. That's really nice. 2.11 times 10 to the 4th equals 2x squared over 1 minus x times 1 minus x. That's going to be fun. So it looks like a quadratic equation, so we can solve through and get x. So there's a whole bunch of ways to do that. You figure out which way works best for you. I might tell you that if you work your way through the math, x is going to equal 0.986 or 1.01. And this is our x value, so we come back over here and this 1.01 will not work because that would give us negative values for concentrate or for x's. And so that tells us that 0.986 is what our x is. It says what percent of hydrogen is converted to HCl. So we're going to take the moles of hydrogen that so partial over total change. So 1 mole to begin with, 0.986 times 100. So we get 98.5% of the hydrogen was converted to HCl. It's a fairly large amount, which makes sense since we had a relatively large Kp. We'll talk more about what large and small means later. Sorry about that.